All right. Well, I think I'll get started. Yes, that'll help. Thank you. So today's lecture is going to be actually a little bit different than the ones that we've done so far. So far we've covered a lot of the foundational material on reinforcement learning algorithms, imitation learning methods, inverse RL, and so on. Today we're going to talk about transfer and multitask learning. Unfortunately, there isn't actually like known good ways to do transfer and multitask learning that just work every time. Instead, there is a large collection of recent research, and because there isn't really one solution to any of the problems that I'm going to describe, instead of giving sort of an in-depth discussion about any particular algorithm, what I'm going to do today is instead actually give a high-level overview of a collection of papers that are representative of certain classes of techniques in this field. So today's lecture is going to be probably quite a bit more high-level than the previous few, and really its purpose is to give you an overview of the field so that if you find yourself needing to solve a transfer or multitask learning kind of problem, you'll sort of know which general keywords to look for and what sorts of papers to go and read. So you know, there won't be that very much math here at all. It'll really be aimed at providing you with a survey of recent literature. Next week, we're going to have a lecture on meta learning. It'll actually be a guest lecture given by Kate Rakelli, who's a PhD student who's done quite a bit of work on this topic. And Kate will go into a little bit more depth about a particular class of multitask learning methods, which are meta learning methods. Next week on Wednesday, we'll also have a guest lecture. We'll actually have two guest lectures on the same day. One from Richard from the RISE lab, who will talk about systems for reinforcement learning, and another one by Jason Peng, who will talk about advanced imitation learning methods. So next week on Monday we'll have meta learning, and on Wednesday we'll have systems and advanced imitation. But today we'll do transfer and multitask learning. All right, so today's lecture, I'm going to talk about how you can transfer knowledge from prior tasks to learn new tasks more quickly. I'll discuss forward transfer, which is where you train on some source task in such a way as to do better on a target task. I'll talk about a particular type of forward transfer that's based on randomization and a few examples of papers that have studied this. Then I'll talk about multitask transfer, where you use variability across different training tasks to get models that can generalize more readily to new tasks. I'll talk about contextual policies, and then I'll talk about modular policies pretty briefly. So the goal for today will really be to understand at a high level the landscape of research on transfer learning and multitask learning. All right, so what's the problem? Let's think about some Atari games, since you guys are probably pretty familiar with these if you're not completely sick of them at this point after homework 3. So for homework 3, you guys implemented your Q-learning stuff and ran on Pong. If you want to go for some brownie points, you might have also tried it on a whim on some other Atari games. Maybe you didn't, maybe you did. Here's a different Atari game. This is called Breakout. Like Pong, this game is pretty easy to learn with Q-learning. So you run your Q-learning algorithm. You can try it after this lecture if you want. Just load up your homework 3 code, change the game from Pong to Breakout, and you'll probably find that your Q-learning code can learn the game Breakout. It probably takes a bit longer than Pong, but it's generally fairly easy. If, however, you change the game, instead of changing it to Breakout, you change it to a different game called Montezuma's Revenge, you might find that it doesn't really work. So here's an animation of Montezuma's Revenge. It's this little guy. He's supposed to be plundering the treasure of some ancient peoples who built a pyramid, and for some reason there's a little skull in that pyramid and the key and doors and things like that. The games kind of look fairly similar, but the one on the right is much, much harder. So why is it so much harder? Well, partly it has to do with how the game works. So you, in Breakout, you get a little point every time you break one of the bricks. So it's pretty easy for the agent there to learn that breaking bricks is good and you should just keep breaking more and more bricks. In Montezuma's Revenge, things are a little more complicated. Like you get some points for picking up a key, but there's only really one key, so picking up that key doesn't really help you so much with other stuff. You get some points for exiting the door, but these rewards that you get don't really provide the kind of trail of breadcrumbs towards winning the game in the same way that the Breakout one does. So in Montezuma's Revenge, getting key gets you a reward, opening a door gives you a reward, getting killed by the skull is bad. It doesn't actually give you negative reward, but if you die too many times, then you lose. You don't have any more lives left, so then you lose the game. So there are a bunch of these things, and they seem kind of arbitrary, and they don't necessarily put you on the path towards winning the whole game, which requires traversing through these different rooms and getting to the bottom of the pyramid and so on. So we'll talk a lot more about how to deal with these kinds of problems where the rewards don't quite give you good guidance about how to succeed at the task. We'll talk about this a lot more when we discuss exploration 2 weeks from now. But for now, I actually want to focus on a different facet of this problem. See, to us, when we watch this little animation for Montezuma's Revenge, it might not occur to us why this is so hard for our Q-learning agents to learn. Because to us, this kind of makes sense. Like, you want to go through a door, you pick up a key. So we kind of know what to do in this game when we play it ourselves, and you can load up the Atari emulator and play it yourself. I think it's kind of a fun game. It's interesting. We know what to do because we understand what all these little pictures mean. So we understand that keys open doors, and that you can climb on ladders, and that if your goal is to get to the last room in the pyramid, going through doors seems like a semantically meaningful way to get there, because doors are what bring you from one room to another room. In fact, we even know that a skull is something bad. We might not know what exactly this skull does because we haven't encountered a giant rolling skull before, but we kind of associate the symbolism with something negative. Like, it's probably a pretty good guess when you see this animation that like the goal is not to touch the skull repeatedly. Like, that seems like probably a bad thing. So something that we know from our past experience helps us figure out new tasks much more efficiently, and in this case, dramatically more efficiently than the RL algorithm, to which these are all just masses of pixels, and a priori the key is not any different from the skull, just a different mass of pixels. So prior understanding of the problem structure can help us solve complex tasks much more quickly. And that's the basic idea behind transfer learning. It's to use structure, knowledge gained from other tasks to solve new tasks more efficiently and more effectively. So, for instance, if you want to play Montezuma's Revenge, maybe you've watched Indiana Jones, and from that you've figured out the proper procedure for plundering ancient treasure from burial sites, right? So you have some source of prior knowledge from prior tasks that you've done, or even just prior sources of information that you've gathered. So if you've solved prior tasks, you might acquire useful knowledge for solving a new task. Now, where is that knowledge stored for a reinforcement learning agent, right? For us, it's stored in our memory. We've watched Indiana Jones. You remember what he did to plunder the treasure, and then you can remember that and use that experience. But where is that knowledge stored for a reinforcement learning agent? Well, it could be stored inside the Q function. So the Q function tells us which actions or states are good states and actions. So it might figure out that even if it doesn't know how to climb the stairs, maybe if there is a state where you're holding the treasure, like over here, that's a good state. So if it sees you transitioning into that state, it'll say, oh, that's also a good thing. So the Q function can hold some of that knowledge. It might hold that knowledge in a policy. So it might learn that some actions are just potentially useful actions. Maybe it doesn't learn about all the actions that you need to solve this new task, but might figure out that some of them tend to be good, some of them tend to be bad. Maybe it knows that things involving the skull are bad, so it shouldn't walk into the skull, even if it doesn't quite know how to exit the door, if there's some past task that involved a skull. The knowledge can also be stored in a model. If you're doing model-based reinforcement learning, maybe the task has changed. Maybe before your task was to steal that little golden idol, and now your task is to exit through the door, but something about the physics of how the world works may have remained the same. So perhaps ladders still work as ladders and keys still work as keys, even if what you're trying to accomplish in the environment is now different. So the model can be a great way to transfer knowledge from one task to another. And then another one that's a little bit more abstract, but potentially quite important, consists of the features inside the models that are trained. So maybe you've trained your Q function to solve a variety of different tasks, and in order to solve all of those tasks together, that Q function inside of it needed to recognize some visual features. So maybe you played other games that also have keys and skulls, but the games work totally differently, the actions are different, but nonetheless, the keys and skulls are still salient, So maybe your model will learn some feature representations that extract where the skull is and where the key is, represent those somewhere internally inside the model. So then if you can reuse those features to solve a new task, you might learn that new task much more quickly by using those features. And this is actually something that shouldn't be underestimated, because oftentimes some very interesting and very abstract understanding of the task can be stored inside the features of a neural network. As an aside, here is a fairly vivid illustration of this point from a paper by Evan Shellhammer called Loss is its own reward. So in these experiments, what Evan did is he trained a Q-learning, actually I think this is an A3C agent, to play a variety of different Atari games. And that's shown via the black line, so that's just a RL algorithm running from scratch. And then what he did is he took the trained network, he cut off the last layer, so the last layer is the one that maps the last set of activations directly to the Q values and to the policy's action probabilities. Remove that layer, which makes the network unable to produce good Q values or good policy probabilities, but still retains all the visual features. And then he retrained the model, essentially just retrained that last layer from a random initialization, but reusing the features learned from a successful run. And that's shown via the red line. And you can see that for all these games, the red line learns a lot quicker, which suggests that those visual features inside the convnet did actually retain useful knowledge, useful representations for the task. Now this is maybe a little bit more of a trivial experiment because, clearly weights that were previously learned for that game should be useful for that game, but it does show that there is some gains to be obtained from the ideal representation. Okay, so a little bit on the terminology for transfer learning. So I'm going to discuss a variety of different methods, a variety of different research papers, but many of them will share similar terminology. So transfer learning refers to using experience from one set of tasks for faster learning or better performance on a new task. And if we're talking about reinforcement learning, task here means MDP. Question, yes?
Sorry, this might be more of a trivial question, but I wanted to ask you, could you give an example of a feature for a game?
Right, so the question was, what's an example of a feature for a game? So let's think back to Montezuma's Revenge, right? So you have a setup like you did in Homework 3. So in Homework 3, you have your image from the Atari game. It goes into a convnet. So this is a convnet with a few layers, and then there's maybe like a fully connected layer or two, and then you get your Q values for the different actions, right? A0, maybe you have 3 actions, so you have 3 scalar values that are getting outputted. So when I say features, what I mean is some layer inside this network. So maybe you just pull out the last convolutional layer, and those are our features. So if you have an image coming in, I, this is phi I, and then these things are going to be like WA0 transpose phi I, which is basically just a linear layer. So that experiment that I showed from Evan Shellhammer's paper essentially just cut this off and then reuse the phi. So the phi is where the features live. And you could take different layers in the network, and that will just affect the complexity of the features that you get, with simpler features early on and more complex features later on. All right. So in transfer learning, our goal is to transfer experience from one set of tasks to a new task. A task is an MDP, and the source task and the new task can differ along different aspects of the MDP. So they can differ in terms of the dynamics that they have, in terms of their transition probabilities. They can differ in terms of their reward function. They can differ simply in terms of their initial states. So we call the task that we train on initially, the task from which we are transferring experience, the source domain or the source task. And then the new task that we want to solve is referred to as the target domain or the target task. So your goal is to transfer knowledge from the source domain into the target domain. And oftentimes, when people talk about transfer learning, they'll use the term shot to denote the number of attempts in the target domain. So for example, if you've learned a highly generalizable policy, typically from a couple of different source domains, from maybe a large number of source domains, and that policy is so powerful and so generalizable that it can solve a new target task on the very first try, then we would say this is a zero-shot generalization or zero-shot transfer, meaning that without having attempted the task even a single time before, it is already successful in the new domain. So if someone says, oh, my algorithm is doing zero-shot transfer, what they mean is they trained it in the source domain or source domains, and then it just works in the target domain. Now, this typically requires some assumptions about the similarity between the source domain and the target domain. If someone says, oh, my algorithm is doing one-shot transfer, what they mean is it attempted the task once in the target domain, and from that it was able to figure out how to solve the task. And then if they say, oh, my algorithm is doing few-shot transfer, what they mean is it attempted the task a few times in the target domain. There's like a little bit of jargon that people tend to use in transfer learning. Don't be confused by it. It just means this. OK, so how can we actually set up the transfer learning problem? Well, there are a few different formulations, and they'll all give rise to different methods. So you could think of transfer as forward transfer. So forward transfer means you train on one task, and then you just go and try to do a new task. You could do sort of naive forward transfer, like literally just train on a task and then go do another task. And I'll refer to this as the tried and hope for the best method, which works if the tasks are similar enough, but it's a little hard to say anything terribly concrete about it. A much more reliable thing to do is to train on one task and then fine-tune on a different task. And there are actually a few things we can do to make that more likely to succeed. Another thing you could do is, if you have some control over the source task, you can actually select the source task carefully in such a way that transfer is more likely to succeed. So one of the things we'll discuss that actually makes this work better is to introduce some degree of randomization to the source task. The rationale there being that more diverse and broader source tasks are likely to result in models that generalize to new tasks. So we'll discuss this in a lot more detail. Another thing we can think about is multitask transfer. In multitask transfer, there are actually two potential goals that are a little bit different. One goal, which is maybe the more obvious one, is to train on many tasks so that you get something that can succeed on a new task. Another more modest goal is to simply train on multiple tasks simultaneously in the hopes that learning the tasks together accelerates the learning on all of them individually. So if you have like 5 tasks that have a lot of shared structure, maybe you can actually learn those 5 tasks jointly more quickly than if you were to learn each of the 5 individually. So we'll talk about randomization. We'll talk about how model-based reinforcement learning can be a pretty good idea for multitask transfer. We'll talk about model distillation. I've actually discussed this a little bit back when I talked about model-based RL, but I'll revisit it here. We'll talk about something called contextual policies, which will actually come up again in the meta-learning discussion next week. And I'll talk about modular policy networks. All right, and then next week we'll learn about multitask meta-learning, which sort of takes this multitask transfer idea a step further and says that instead of just trying to transfer the model itself, transferring the value function or the policy or the dynamics model, in meta-learning the goal is to actually transfer a learning strategy, so to actually learn how to learn from past tasks so that you can do that few-shot learning more efficiently. So that'll be covered next week. And the thing that I'd emphasize here is that there isn't really a single solution to these problems. So this is very much an active area of research. And as I mentioned at the beginning of the lecture, the goal of this portion is really to give you guys a broad overview of the kind of things that are going on in the field, so that if you do want to tackle transfer learning or multitask learning problems, you'll have some idea for where to get started. All right, so let's talk about forward transfer. So forward transfer refers to the case where you have a source domain, you'd like to do something in that source domain, learn something, and then try to see if you can get better performance in a target domain. So, the most obvious thing to do is if you need to evaluate your RL policy or model or value function in a new domain, is to train in your source domain and see what it does in the target domain. So this is you can say this is the tried and hope for the best method. And policies trained in one set of circumstances might just work in a new domain, especially if the circumstances in the new domain are sufficiently similar, but there aren't really any promises or guarantees that you can make about this. So an example is when I was actually doing my postdoc, I did some experiments. I trained up a little policy to put a little cap on a bottle, and then I thought, well, wouldn't it be nice if it actually worked if I put in some other bottles in the background? And I was pretty happy because it worked. And then I thought, well, wouldn't it be nice if I could hold that bottle in my hand and see if the robot could still figure it out? And then it turned out not to work. So trying it and hoping for the best sometimes worked and sometimes didn't. Here maybe it was a little bit confused because my sleeve is kind of the same color as the arm, so I thought, oh, maybe this is there's something different going on here. Okay, so a few years passed. Since then we got a little bit better at training policies that generalize, but same general story. So this one is trying to pour the nuts into a cup, and sometimes it works, and then sometimes it doesn't. So try and hope for the best will sometimes work and sometimes won't. Something that's a little bit more secure, that you can count on a little bit more often, is fine-tuning. And in fact, fine-tuning is actually the most popular transfer learning method in supervised learning. Question, yes?
It's kind of a tangent, but on the video it said the policy attended to some other object.
Yeah, so I didn't really describe the method too much, but the thing that made this guy work better than this guy is that over here there is a sort of an intentional mechanism using some object detectors that's actually trying to pick up on the cup. And when there are multiple cups, it gets a little bit confused because then it attends to both of them, splits the difference, and ends up going in the middle. All right. So yeah, in regular supervised learning, if you're faced with a transfer learning problem, actually probably the first thing that you will try is some form of fine-tuning. So fine-tuning refers to essentially the thing that was described in that slide from Evan Schellhammer's paper, where we train a model to do the source task, and then we'll either cut off the top layer of that model, or if the output size is the same, we might even keep the top layer, and then we simply train it some more on the target task. It's a very, very simple technique. It's in some sense almost the most obvious thing you can do. Train on the source task and then train some more on the target task. In supervised learning, this tends to work very well if the source task is pretty broad and pretty diverse. So for example, if you're doing computer vision, if you pre-train on, let's say, classifying the 1,000 categories in the ImageNet large-scale visual recognition challenge, that model might be pretty well suited for fine-tuning to recognizing some new object categories, because those 1,000 training categories in the source domain might have forced the model to acquire visual features that are just generally useful for classifying objects. And this is, by the way, there's a theme here that you'll see again and again, that a lot of the methods that we use for transfer learning and multitask learning in RL are really extensions on methods previously developed for transfer learning and multitask learning in supervised learning domains. So we might be tempted to think that we could use fine-tuning directly in reinforcement learning, but there are a few challenges. So the regular formula for fine-tuning is pre-train on some really large source task like ImageNet classification, and then fine-tune on whatever your target task is, like detecting parts of birds, for example. That tends to work very well if the source task is extremely broad and diverse, like ImageNet classification. The trouble is that we don't really have a notion of ImageNet features for RL. We don't have typically tasks that are quite as broad and diverse as the ones in computer vision. So in RL, the tasks are generally a lot more narrow. Like, for example, if you have the little ant locomotion thingy that you guys had in homework 1, well, it's a little hard to imagine that pre-training on ant locomotion tells you something useful for getting this thing to jump, for example, because maybe jumping is just too different from running. So the features that you get are generally a bit less general if you have a narrow task, and they therefore will not actually always give you useful knowledge for target domains that are too distinct, for target MDPs that are too distinct. The policies and value functions can become overly specialized and so forth. There's another somewhat more subtle problem, which is that if you have a fully observed MDP, there is always an optimal policy for that fully observed MDP that is deterministic. And typically, the reinforcement learning algorithms that I described so far will actually find a deterministic policy. They might not find one that is perfectly optimal, but they'll typically find one that's deterministic. Especially policy gradient methods, because for policy gradient methods, they'll figure out pretty quickly that a good way for them to increase their expected reward is to decrease the amount of randomness, to decrease the entropy of the action distribution. Because if they decrease the amount of randomness, if one of the behaviors is better than the rest will become less likely, the good one will become more likely, so they tend to become more and more deterministic. And that's actually pretty bad news for fine-tuning, because if you then take those nearly deterministic policies and you put them into your target domain, they will not explore very much. They will not try things that are different than that single good thing they found in the source domain. So they lose exploration and convergence, and as a result, adapt very, very slowly to new settings. So this second factor can actually be a big problem for fine-tuning in RL, even if your source domain is structurally very similar to your target domain. So the games that we're going to play when we try to get fine-tuning in RL to work better will essentially all revolve around the goal of diversifying the training, the source domains, and broadening the entropy of the policy. So you want source domains that are more varied, you want to solve those source domains using more varied strategies, and you want to acquire a policy that is more stochastic than what you would usually get. And generally, things that increase the diversity and randomness for that source domain and the resulting solution will improve performance for fine-tuning. So one thing that we actually already discussed last week for facilitating this is the connection between reinforcement learning and inference. So we discussed this particular model for optimal control that explains why you might not always do the perfectly optimal thing, but might instead be a little bit random. And on Monday, we talked about how this can allow us to acquire inverse reinforcement learning methods. Last week on Wednesday, we talked about how you can also use this as a forward reinforcement learning algorithm. And the forward reinforcement learning algorithm has an interesting property, which is that it optimizes the expected reward plus the entropy of the policy. I went through this pretty quickly last week, but I'll elaborate on this point a little bit more today. When you maximize the reward and you maximize the entropy, you get a policy that is worse at the source task, worse in the sense that it will not get as high of a reward. In practice, actually, adding this entropy term sometimes makes things better, because even though you're optimizing a slightly incorrect objective, you're exploring more and might reach a better optimum. But more important for today's discussion, it might actually give you a policy that is more well suited for fine-tuning. And I'll illustrate this with a little example. So let's say that you have this little task. So you have the little ant robot from before, and it has to navigate this maze and reach the blue X. If you run regular reinforcement learning, and regular reinforcement learning works the way it should, then this guy will take the one path, typically the shortest one, and if there are multiple paths that are equally short, it'll break the tie in some arbitrary way, but it'll end up with a single strategy. So maybe if I train it on this maze, it'll go up and to the right. If I run maximum entropy reinforcement learning, if I basically do this thing, then the policy will be incentivized to solve the task in as many ways as possible, because solving the task in more than one way will allow it to have a higher entropy. So if there are multiple paths through this little environment that all reach the goal, it'll actually be a better solution, a better maximum entropy solution, if it can randomly select among those different paths. Maybe the lower one is a little longer because it has to go south, then east, then north, so it might have lower probability, but still non-zero probability. So perhaps if I run maximum entropy reinforcement learning in this environment, I'll actually get a policy that maybe 70% of the time goes up and then 30% of the time goes down and explores both paths. Now, if my target domain is a little different from the source domain, maybe in the target domain there's a little wall over here, now my maxent policy will still succeed occasionally, not very often because the more likely path, the upper one, has been blocked, but that lower one still has maybe 30% probability, and if I just run that policy a bunch of times, it'll succeed a few of those times. If, however, I use the regular deterministic reinforcement learning algorithm that only ever executed that upper path, then when I bring it to the target domain, it'll never succeed, and it will essentially be no better off than if it was learning from scratch. So this is sort of the intuitive explanation for why maximum entropy algorithms can actually produce policies that are more well suited for fine-tuning, because they aim to solve the task in the source domain in as many ways as possible, rather than just the single best way. Any questions about this? Yes?
So if you fine-tune it, in the target domain, would it eventually only take the bottom path and never take the top one?
Right, so in the target domain, you would expect that this top path maybe has a reward of like 0, and that bottom path has a reward of 100, whereas in the source domain, they both have a reward of like close to 100. So in the target domain, once you fine-tune it, it'll stop going up. But it's a lot easier for the policy to figure out, among these two things that you already know how to do, just stop doing one of them, as opposed to unlearn the thing that you're doing and then learn a completely new thing. Yeah.
Are you still maximizing entropy during the evaluation process, or is it just during training?
Right, so the question is, are you still maximizing entropy during the evaluation process? This is sort of a slightly controversial issue. So in practice, if you wanted to just get this to work, probably okay not to worry about it too much, to just maximize entropy both during pre-training and during fine-tuning. In practice, once you fine-tune and you really want the very best performance you can get, then having less entropy will make it better. And there are a few things you can do there, some more principled and some more heuristic. The principled thing to do is to put a little multiplier on this, so put a little coefficient alpha in front of this entropy, and then gradually reduce that coefficient. The slightly less principled thing to do, which still tends to work really well, is that if you have, let's say, a policy that is represented as a multivariate normal distribution, a Gaussian distribution, where the mean is given by a neural network and the variance is given by a neural network, then just force the variance to 0 at test time. That's not actually guaranteed to work, because you didn't train it for 0 variance, you trained it for some non-zero variance. But in practice, it might work decently well. Yes?
It seems like the success of transfer learning depends on like how similar your target and source domain is. Is there like a principal way to quantify the difference between two MPPs?
Right. So the question was, well, it kind of seems like the success of transfer learning is quite dependent on the similarity between the source and target domain. Is there a way to quantify this similarity? I'm not actually aware of any particularly general way to do it in the single task forward transfer case. In the multitask transfer case, there is actually a way to do this. The idea that you can use in multitask transfer, which Kate will discuss a little bit more next week, is that you can assume that during training, you actually train on a distribution of MDPs. So you have some P of M. And then when you transfer, what's really happening is that a new MDP that you haven't seen before is sampled from that same distribution. So a practical example of this is, well, let's say that I'm learning to navigate through buildings. So I'm going to train in 20 different buildings, and then I'll transfer to the 21st building. If those buildings are selected uniformly at random from the set of all buildings in San Francisco, then I might expect that test building to come from the same distribution, and therefore if I train on enough buildings, I will generalize to another one from that same distribution. So this applies for the multitask transfer setting. For the single task transfer, it typically ends up being a bit more ad hoc. Any other questions? Okay. So this is a video that I actually showed last week on Wednesday. This is an example of transfer with maxent RL. So this terrifying Halloween-appropriate video shows the ant robots on the right side here learning with maxent with a reward that just says run fast. And when the reward is to run fast, they will run fast in all the ways that are possible, which means they'll run in all possible directions. So when they've learned to run in all possible directions, and we then fine-tune them to run down a particular hallway, now all they have to do is essentially forget how to run in all directions except for south. And that's a much easier thing to do than to learn how to run from scratch, or to unlearn whatever they learned with the deterministic algorithm and relearn running south. And the quantitative results reflect this also. So if you want to know more about fine-tuning in RL, here are a few potential references. So the maxent paper that I mentioned, that's this one by Harnoy and Tang. Another method that you could check out, so remember how I mentioned that when we transfer, we can transfer policies, Q functions, You can also transfer models, and you can also transfer features and representations. So this first one, the Harnoy and Tang paper, transfers policies and Q functions. This second paper by Higgins et al. Actually transfers features trained from source domains using, in this case, a variational autoencoder. Another very popular class of techniques for pre-training and fine-tuning is to use hierarchical methods. So these are methods where you use the source domain to acquire an ensemble of primitives, which you can then either fine-tune directly in the target domain or train a higher level to select among the primitives in the target domain. I won't talk about this too much today, but if you want to learn more about it, you can check out maybe these two papers to start with, as far as kind of recent papers on this topic. So that's for the hierarchical stuff. And there are, of course, many, many others, but I want to just mention a few in case you guys want pointers to get started. All right, so far we just kind of assume that we have a source domain that is given to us, and we just want to do something in that source domain that will prepare us to transfer to a given target domain. But in many cases, we actually have some ability to manipulate the source domain, to actually choose a source domain that is more suitable for what we want. So what if we can design our source domain to some degree, and then we know that we have some difficult target domain that we haven't seen yet? How do we choose the design of our source domain to maximize the potential for transfer? This is often the case, for example, if you're imagining training a policy in a simulator and then trying to get it to transfer to a real-world task. So you get to design the simulator, but you don't get to design the real world. The idea at a high level is actually going to be very similar. The more diversity you see during training, the more likely it is that transfer will succeed. So essentially, if you see a wide variety of different situations in the source domain, you're more likely to see something that will also happen in the target domain. If you see a very narrow range of situations in the source domain, then you might not cover those kinds of situations that the target domain will present to you. So the first paper I'll discuss that kind of does some variant of this, that exploits this idea, is a paper by Rajaswaran et al. Called EP-opt. And this paper is concerned with randomizing physics parameters. So the idea is this, that if you have a little hopping robot, like the one that you had on homework 1, and you want to train with one particular physical configuration of this hopping robot, and then you'd like to transfer to a version of this hopping robot that has maybe a lighter upper body or a heavier body, so some kind of physical variability. If you just train with the normal hopper and then transfer to a lighter hopper, chances are it won't work, right? Because your policy that you train over there on the left will be pretty narrowly adapted to this particular configuration. But if you train on a variety of different hopping robots, then maybe your policy will learn to be robust to that factor of variation. So it's a very simple idea, also very widely explored in areas like robust control. And this can be confirmed experimentally. So what these plots are showing, on the x-axis is the mass of the torso of the little hopping robot, so the mass of this upper link. And these three plots, and on the y-axis the reward. And the three plots show the performance for different torso masses of a policy trained with a single mass. And that single mass is indicated in the legend here. So this one was trained with a mass of 3, which is over here. This one was trained with a mass of 6, right there. And this one was trained with a mass of 9. And unsurprisingly, when you test it on the same mass that it was trained on, it does very well. And as the mass becomes more and more different, it does much worse. So if you train on a mass of 6 and you train with and you test with a mass of 9, it'll do quite poorly. That's not at all surprising. Now, conventionally, the sort of the belief in the field of robust control is that you can robustify your policy against these kind of variability by training on a variety of different masses, but you will pay a price when you do that, because if you have to be robust to a particular parameter, you'll probably get lower performance overall. And that's a very reasonable sort of view of the world, especially when we consider policies with very limited representational power, like linear policies. One of the things that's kind of interesting about deep neural network policies is that while this trade-off in principle still exists, in practice, it tends to be a lot less severe. So if you actually train a deep neural network policy on a variety of different torso masses, for this particular task, which is a fairly easy task, admittedly, you actually will see essentially no degradation in performance. So what this curve is showing is a policy of the same exact size as these policies, trained on an ensemble of masses. The distribution of the ensemble is given by this Gaussian. So it has a peak over here at 6.5, and then a little bit of a variance. And the purple line shows performance across different masses. And what you can see there is that the purple line is at the same height as the best performance for each of these three. So the actual loss in performance from training the policy for robustness, in this case, is actually non-existent. On more complex tasks, you will see some loss, but it tends to actually be a lot lower than you might imagine. And of course, the benefit is that it works for all masses. So this is an interesting observation, and actually is sort of one of the ways in which deep RL is a little bit different than standard shallow or linear control methods, that you can actually use the expressive power in that model to get robustness with minimal loss of performance in some cases. Now, in practical transfer situations, one of the things that we often care about is not just whether we can generalize across variability in some known parameter, but whether we can generalize even when there are unmodeled effects, meaning that there are some things that change between the source domain and the target domain that are not varied in the source domain. Maybe because we don't know what those things are. Maybe our simulation simulates some physical phenomena but not others, and then in the real world there are new physical phenomena that we didn't expect. So maybe I simulated my robot assuming that it had, kind of Coulomb friction at the contact point, but maybe in the target domain there's like also differences between static and dynamic friction, and maybe the foot is like a little bit soft and deformable, whereas my simulation was perfectly rigid. So I might have some unmodeled effects. And of course, we always have unmodeled effects in reality because we can never build a truly perfect simulator. So what's interesting is, well, what happens if we intentionally don't model variability in one of those parameters? Maybe we pretend as though we didn't realize that mass can vary, and we only vary things like friction coefficients. Can we actually get good transfer that way? And it turns out that we actually can. So what this plot is showing is the difference between maximum likelihood system identification and training with an ensemble. So a very conventional and obvious way to tackle this sort of problem is to say, well, let's just estimate the parameters of my simulator to get the highest accuracy to the real system. So I'll generate a few trials in the target domain. I'll estimate the parameters that produce trajectories that are as close as possible to those trials, and then I'll train on that. So that's what is labeled as maximum likelihood here, shown by the green line, and that's a conventional system identification approach. The ensemble approach here says, even though you have this set of parameters that seem to be the most accurate, let's just intentionally broaden that range. Let's randomize it more to get you to be a bit more robust. And that tends to be quite a bit better in the presence of unmodeled effects, which in this case is the mass. So you can test a little bit, adapt, and still randomize. If you actually look at what that ensemble ends up learning, it's a little bit interesting. This is a toy example where we just varied the torso mass and the friction. And what these iterations are showing is different iterations where the distribution over the randomization parameters are adapted. So iteration 0 is just some random blob. Don't worry about that. And then iteration 3 is after you've adapted that distribution. And something interesting here is the red X shows the true parameter setting in the target domain. And the distribution is kind of a little bit spread out. And you might wonder, well, why is it spread out in this kind of diagonal fashion? Like, why does it seem to spread out in this direction? Well, it's because if you decrease the mass, you get a lower normal force. And when you get a lower normal force, you get a lower frictional force, because the frictional force is the friction coefficient times the normal force. So decreasing the friction coefficient actually affects the friction force in a similar way as decreasing the mass. So what this thing figured out is that, yeah, your mass can be like a little bit lower and a little bit higher so long as you adjust the friction coefficient accordingly. And that'll kind of produce similar looking physical variation. And that actually illustrates part of why this unmodeled effects stuff actually works. The reason that it works is that varying other modeled phenomena can produce changes in behavior that perhaps capture some of the changes that you get from the unmodeled effects. So if you have some effects that are unmodeled, but you vary enough of the other parameters, you might actually still see behavior that is close enough to what you get with the unmodeled effects. Which means that if you randomize enough physics parameters and train a policy that is robust to them, you might actually generalize even in the presence of unmodeled effects in the target domain. All right, so far, this particular method relied pretty much entirely on training a feed-forward neural network policy that could just like manage whatever mass or friction or damping parameter the simulator threw at it, which is sometimes possible but sometimes not possible. You can improve your odds by using a smarter policy design. So this paper, called Preparing for the Unknown, proposes actually a pretty clever design where you combine your policy with a little recurrent neural network that essentially tries to figure out what the current simulator parameters are. So here we vary the simulator parameters, but we don't tell the policy anything about what's going on, and we just say succeed for all possible parameters. Here, what we're going to do is we're going to actually have a little system identification recurrent neural network, which will read in a sequence of states and actions that we've experienced before, and try to actually predict the physics parameters, and then feed those physics parameters into the policy. So if the policy knows what the physics parameters are, then it can, of course, do a lot better. In practice, in the target domain, you do not know what they are. But if you train up this little recurrent neural network to predict them, then you might do quite a bit better than if you had to have a policy that is required to do well for all possible physics parameters without knowing what they are. So if this RNN does a good job, predicts the right parameter value, and the policy learns how to make use of it, then in effect, the RNN will do a little bit of online system identification as it's performing the task in the target domain. And this paper evaluates it on a few simulated environments, like a simulated version of the Hopper, which is more stylish and rectangular now. And what this curve is showing is on the x-axis, kind of similar to the plots on the previous slide. On the x-axis, it's varying a particular physics parameter. The particular parameter here is the offset of the center of mass. So you kind of artificially take the center of mass and you shift it backward and forward by some number of meters. The blue line shows a regular policy that is unaware that this is happening. The green line shows a policy that is provided with the true value of that parameter. So it's sort of a cheating oracle policy, meant as an upper bound. And the red line shows their online system identification policy, which uses the RNN to predict that parameter. And you can see that the red line is pretty close to the green line, which means that their RNN is doing a good job of actually guessing this physics parameter. Now, in this paper, they present a fairly simple version of this idea where they vary maybe one or a few parameters at a time. And they actually supervise their recurrent neural network with the true value of that parameter. So they assume that at training time in the source domain, they know what the value of that parameter is. In the target domain, of course, they don't have to know that because the RNN will predict it. It turns out that this idea actually works even if you simplify it a little bit. So this is work that was sort of a follow-up to this a few years afterwards by Jason Peng, where what Jason did is he essentially had a version of this where during training in the simulated source domain, the policy is not actually provided with the ground truth physics values, but it's just trained end-to-end with reinforcement learning. So the RNN just looks at the history of states and actions and is just asked to output some hidden vector that will allow the policy to get high reward without supervising it with the specific physics parameters. And that turns out to also work. So this was a robot trained in simulation and then tested on pushing this thing that looks a little bit like a birthday cake in the target domain in the real world. All right. So the same idea can actually be used not just for physical variability, but also for visual variability. And in this regard, this idea is actually a little bit closer to something that, again, has been quite popular in the supervised learning world, which is data augmentation. So data augmentation refers to taking some images and maybe randomizing their colors, randomizing their orientation, randomizing their a linear crop. This is going to apply a similar idea to vision-based reinforcement learning. So in the same way that we randomized physical parameters like friction and mass before, now we're going to randomize appearance parameters. So sort of the question here is, well, if you want this little drone to fly through a hallway, this is Quarry Hall across the street, what kind of simulator should you build? Should you build a very high-fidelity representation of Quarry Hall, or should you just build simulators that are randomized and diverse enough so that Quarry Hall is in some sense in the convex hull of all possible simulated environments? And that's what this paper tried to do. So these are the simulated images that were generated there, and you can see that these simulated images look a little bit silly in some cases. So some of them look kind of reasonable. They have some brick walls. Some of them have like weird pink floors and so on. So they're not really meant to be very realistic. They're just meant to be highly varied. And the idea is that if you train your vision-based, in this case it's a vision-based flight policy, maybe it'll just figure out the features that are conserved across these highly randomized environments, like vanishing points in hallways and things like that, and ignore the things that are irrelevant and randomized, like the texture on the walls. So here's a little fast-forward animation of the training environments. You can see that they're highly varied and not super realistic. Looks like kind of a stylish video game from the mid-1990s. But then if you train in those randomized environments, you actually get a pretty decent policy for flying the drone in the real world. It generally works well, except it gets a little bit confused by windows. So there were no windows in the training setting. So from this, we can conclude that clearly birds are trained in simulation and tested in the real world, because birds also get confused by windows. All right. Now, this idea, has since then been applied in many, many other settings. So both the physics randomization and the visual randomization is actually a very popular technique at this point for transferring from simulation to the real world. Typically done with manual design of the randomization parameters, but there's also been quite a bit of work on automated design and also on using these kind of RNN-style online system identification models. Now, these methods so far have all done kind of blind forward transfer, meaning that the problem is framed as designing the source domain so that whatever policy you get just works in the target domain. But in reality, we usually have a little bit more knowledge than that. We usually do know something about the real world. Maybe we have a few pictures of what the real world looks like, or maybe a few trials from a real world system. So if you get to peek at the target domain, you can actually do quite a bit better than this. And here, again, the techniques, just like before, are very heavily inspired by techniques from supervised learning. So in supervised learning, this kind of stuff is typically referred to as domain adaptation. So domain adaptation refers to a setting where you have a large amount of good data in a source domain, a small amount of data or unlabeled data in a target domain, and you know that those two domains ought to be aligned in some way. So you can train your model explicitly in such a way that it sort of tries to be invariant to the differences between the domains. So far, we've essentially done pure, in the jargon of transfer learning, zero-shot transfer, which means that you learn in the source domain so that you can succeed in some new unknown target domain. In general, this is, of course, impossible, because if you don't know how the target domain varies, you can't really do much to prepare for it. So maybe you'll train your robot in a randomized simulator, but then it'll be tested like on the moon or something in situations that are just totally different than anything you expected. So you have to assume something about the target domain. And if you're assuming something about the target domain, you probably know what the target domain is. And that means that you can probably get a few observations from it. So if you saw a few images from the target domain, maybe you've actually seen these things, you can actually do a bit better than just pure randomization. So one of the domain adaptation tricks that you can do, which is pretty simple, is to do adversarial domain adaptation. So this is a paper that does a little experiment with a robot, and it's doing kind of a funny task. It's taking a hook of rope and trying to hang it on a little grocery scale. I don't know why you want to do this. Maybe you want to figure out how much your rope weighs so that you can figure out how much it costs or something. But anyway, the simulated images look like this, so they don't look very realistic. And they're not randomized either, so maybe whoever designed the simulator was a little too lazy. They didn't bother randomizing their textures. Can we still make it work? Can we train with images like this and get the robot to succeed with images like this? Well, we can actually do that if we realize that these images are supposed to be aligned. So if we basically force the model to represent these kind of images with the same features as these kind of images. And that's the basic idea behind adversarial domain adaptation, also known as domain confusion. The idea is that you impose some kind of loss on the higher levels of your convnet that forces the features for images from different domains to look similar to each other. There are a few ways to do this. If you assume that you have paired alignment, meaning that someone tells you not only are these images analogous to each other, but they're actually exactly the same state. So maybe in the simulator, you command the robot to go to some state and you get this picture. In the real world, you command it to go to that same state and you get this picture, and you know that they're the same. Then you can regularize your features directly to take on similar values. Usually, we don't have that knowledge. Usually, what we would have is some images in the simulated domain and some images in the target domain. They are not directly in correspondence, but maybe we know something a little more general about them, like maybe we know that they come from the same distribution. So perhaps I ran a random policy in simulation and a random policy in the real world. The images are not exactly the same states, but they came from the same policy, therefore they came from the same distribution. If you know that, then you can use an unpaired distributional alignment loss on your features. One example of such a loss, which is very, very simple, is to actually borrow an idea from generative adversarial networks. So if you remember the discussion about GANs from Monday, the idea is that you're going to have some kind of discriminator that's going to try to guess which domain you're in. And is going to guess that, that's what's labeled as confusion loss here, is going to guess that by looking at the features. So it'll look at layer 5 features in the network for real images, it'll look at layer 5 features for simulated images, and it'll try to guess whether those features came from real images or simulated images. And then when we train the network, we'll take the gradient from that discriminator, negate that gradient, and push that into the network, essentially causing the network to learn features from which it is impossible to tell whether you're in simulation or in the real world. So if we think about what that means for this example, it means that if those features represent, for instance, the color of the background, then the discriminator will be able to guess. It'll say, oh, if the background is green, it must be real. If the background is gray, it must be fake. But if they represent the position of the big white circular thing, then it can't tell just from looking at those features whether it's real or fake, because both real and fake images have a big white circular thing located in a similar range of positions. So if you hear the term domain adversarial neural networks, domain confusion, or adversarial domain adaptation, those all basically refer to the same thing, which is putting a little discriminator on the features of your network. You could do something a little more explicit than this. You could actually explicitly transform your images from simulation to the real world or vice versa. It also uses a generative adversarial network, but now this network is actually going to be operating directly on pixels. So that's going to be the idea in this next method that I'll describe. So here there is a discriminator network that looks at a picture. So this time it's not looking at the features, it's actually directly looking at the pixels in the picture. And it's saying, is this real or fake? Meaning, did it come from the real world, or did it come from the output of the generator? And the generator now is not generating images from scratch, it's generating them by looking at a simulated image. So it looks at a simulated image, outputs another image, and tries to get that image that it outputted to be indistinguishable from real images according to the discriminator. So it'll actually transform simulated pictures into real pictures. At this point, some of you might be thinking, well, this is a little crazy, because why do we need the field of computer graphics if we can do this? That's a good question. Maybe we don't. But here's how it works. So this is a simulation. It's sort of state-of-the-art computer graphics from the 1980s. And this is not a real picture. This is actually the transformed picture from the GAN. So this is and here you can see it cut in half. The right side is generated, and the left side is kooky computer graphics. So it actually works decently well. This kind of thing, let me just back up a little bit so you can see the example. So it works best in split screen. And you can actually see that the object, not only does it kind of provide a little bit of shading, it also crumples up the object a little bit, because it says, oh, big flat surfaces are kind of unrealistic, so I'll assume it has like a little crease in it to make it look a little bit more like a real thing. So this kind of stuff actually works. These models are a bit expensive to train, but when trained successfully, they actually can produce very high fidelity pictures. All right, so summary of forward transfer. We talked about pre-training and fine-tuning. How standard fine-tuning in RL is pretty hard. Maximum entropy can help with that, but the basic principle is that you just want to somehow increase the variability of things in the source domain, increase the variability of behaviors, increase the entropy of a policy, all this stuff. And following that same principle, if you can modify the source domain, you can increase variability even more by actually varying things like the physics parameters and the rendering parameters. And if you have a modest amount of data from your target domain, then you can also bring in ideas from domain adaptation to actually either train your network to not be able to tell the difference, or explicitly transform observations from one domain into another. All right, now one thing to keep in mind with these domain adaptation things that I should also mention at this point is that this only provides for invariance. So it assumes that basically all the things that are different are functionally irrelevant. If, for example, the source domain had some functional difference. Maybe in the source domain, that little grocery scale was always like 1 foot lower than it was in the target domain. You wouldn't want to actually eliminate that difference because you need the RL agent to account for it. So the domain adaptation stuff will take care of invariance. It won't take care of functionally relevant variability. All right. If you want some more readings on this topic, here are a few things I might suggest. So this is the physics randomization paper I mentioned. This is the paper that does the online system identification. This is the paper that does the visual randomization. Then there are a few follow-ups that do kind of variants on the same thing in different application domains. So these are a couple of those. This is the domain adaptation thing with the adversarial loss. And this is the domain adaptation paper with that directly transforms image pixels. And there are also, of course, many, many others that sort of look at some variant of this, typically in different application domains. All right, so we have about maybe 17 minutes left. So I'll probably skip the break, and I'll try to cover a little bit of the multitask transfer. But the multitask transfer stuff will be covered also a lot more next week on Monday when Kate discusses meta-learning. So far, when we talked about transfer, we saw this sort of consistent theme that the more variability you see in the source domain, the better your transfer will be. So maybe you can randomize things, maybe you can maximize the entropy of your policy. All this stuff will tend to result in better transfer. So far, we've had to design this diversity into our source domain somehow. We have to like pick the things that we randomize. But what if we had multiple different tasks for training? Maybe if we had enough tasks, even if those tasks might not be directly the same as the task we want to solve in the target domain, maybe just the variability, the natural variability among those different source tasks could facilitate better transfer without imposing the manual burden of having to design that diversity by hand. So in a sense, this is perhaps closer to what people do, right? We don't have somebody who told us, like, here is your randomized simulator, just like play this video game for 3 days and then you'll know how to do everything in the real world. No, we actually transfer knowledge from our own past experiences, typically past experience of doing other things that taught us something about the world. This is substantially harder because those past tasks weren't directly designed to tell us how to solve the task in the target domain, so you have to work a little bit harder to pull out the right knowledge from those previous tasks to actually facilitate learning the target task. And if you're not careful about it, you can get what's called negative transfer, where the stuff you learn from the source domains actually makes it harder to solve the target task. So I'll start with model-based reinforcement learning on this topic, because model-based reinforcement learning actually provides a very simple answer to this question. So if you do want to do a model-based reinforcement learning thing, it turns out that transfer in the multitask setting is actually quite straightforward. So if the past tasks are all different from each other, what is it they all have in common? Well, one idea is that maybe they all have the same laws of physics. So if I learned how to ride a bicycle, and how to ride a skateboard, and how to drive a car, well, the actual physical motions that I actually execute with my body are pretty different in all those settings, but the laws of physics that govern all those vehicles are at some level the same. And if I understand what those laws of physics are, maybe I can make some pretty reasonable common sense inferences like, objects in motion tend to stay in motion, colliding with things is a bad idea and results in a sharp change in momentum, which is a bad thing. So these are all things I can figure out from my source tasks, even if they're pretty different from my target task. So some examples, maybe you have the same robot, but it's doing different chores. So those all have different reward functions, different Q values, different policies, but the same physics. The same car driving to different destinations, maybe very different policy, but again, same laws of physics. Or trying to accomplish different things in the same open-ended video game. So maybe I'm playing some game where there are multiple things I could do. The game is always the same, but the objectives change, so the model will be conserved. So a very simple way to approach this is to just say, well, let's train a model on all the past tasks, and then use this model to solve a new task. If the model is the same, all that changes is the reward function, so if I'm willing to plan through my model, maybe I don't actually need to change anything about my learning procedure. A slightly more complex version of this is kind of like before, instead of hoping that your model just transfers, you can fine-tune it a little bit to your target domain. So you could say, well, maybe when I solve this new task, I will mostly see similar kinds of physical phenomena and similar kinds of states as I saw in the target domain, but sometimes I'll see something a little bit new because I never had to visit those states in any of my source tasks. So there, I'll just fine-tune my model a little bit. And this is easier than fine-tuning the policy if the tasks are very different, but the physics are mostly the same. First, because your model will already be pretty decent in a large chunk of those states, and second, because your model is trained with supervised learning, and fine-tuning with supervised learning is quite a bit simpler than fine-tuning with reinforcement learning. So here's an example. This is going to be one-shot learning. So if you remember from the terminology, one-shot means after one attempt. One-shot learning of some robotic manipulation skills using models trained for other skills. And that one shot will be used to fine-tune the model, essentially. So the setup here is kind of a hold one out cross-validation. So whenever you see the robot doing some task, like this car task, the model was actually trained on all other tasks, except for that one. And then it's fine-tuned on that one task. So here the robot is doing some things, and you'll kind of see that these things are structurally a little bit related. They're all tasks that involve like assemble a thing with another thing. So you can see it kind of goes a little bit slowly. It's figuring out how this thing works, feels around a little bit, and what's really happening under the hood when it's kind of probing the object like this is that it's fine-tuning the model. So that's why it goes a little bit slowly. It fine-tunes the model, but then once it gets it, then it performs the task. Yeah. All right. So that dealt with a setting where you have model-based RL, you have multiple source domains, and you transfer the model into a target domain. Now, I mentioned in the beginning of the lecture that there are sort of two ways to approach transfer learning in a multitask setting. One way to approach it, the more classical one, is where you train on multiple source tasks and then you want to solve a new target task. A different way to approach it, which is maybe a little bit simpler, is to just say you have multiple tasks that all need to be solved, and you're going to try to see whether you can accelerate the solving of multiple tasks by sharing knowledge between them during training. And right, so what I'm going to discuss here is whether you can learn a multitask policy that can simultaneously perform many tasks at once, and actually study whether that accelerates the acquisition of those tasks. One very simple idea to do this is to leverage one of the algorithms that we discussed before in the course and simply construct a single MDP that captures multiple tasks within it. And you can always do this. It's not always a good idea, but you can always do it. So if you have multiple MDPs, you can always construct a joint MDP, and it's actually pretty simple. Here's how you do it. So this is your single MDP, and the way that you generate a sample from that MDP is you first sample from P of S0, then you run a policy which samples from P of A given S at every time step, then the MDP samples from its transition probabilities, then you sample from the policy, and so on and so on and so on. If you have multiple MDPs, all you do is you change your initial state distribution to basically say that part of your initial state is which MDP you're in. So in the very first time step, you'll select a state, and you'll also select an MDP. You don't actually observe the MDP that you're in, although you could if you wanted to. And then the rest of the episode stays within the MDP that was sampled. And this is now a single MDP that subsumes all the others. So if, let's say, to give an example, if you wanted to use this to play 5 different Atari games with the same policy, you can construct one MDP where on the first time step, one of those 5 games is sampled, and for the rest of the episode, the game remains the same. So it's kind of a fairly obvious construction that allows you to embed multiple MDPs into one, no matter how many you have. This is the most obvious and the most direct way to do multitask learning in RL. But it can be very hard because actually getting reinforcement learning to stuff the knowledge about all of those MDPs into a single policy might prove to be a challenging optimization problem. So we actually saw, back when we talked about advanced model-based reinforcement learning, an alternative way of doing this, where you actually train on each MDP separately and then combine those policies into one via a policy distillation style approach. So the particular thing that we discussed before was this paper, the actor-mimic paper, but there are a number of other papers that have essentially similar ideas. The idea is that you train policies for each of the domains, and then you somehow train a single policy that combines the knowledge from those domains typically with a simpler learning algorithm like supervised learning. So for the actor-mimic paper, the objective is essentially a behavioral cloning objective, where instead of training on demonstrations, you train on samples from the policies that learned to control the individual MDPs. Now, the algorithm itself I covered before in the advanced model-based RL lecture. What I want to show you now is the capacity for this method to actually facilitate transfer. So this is that second kind of transfer, where by learning in multiple games, we can actually accelerate the acquisition of the policy, among the different games by sharing knowledge. And that's what these graphs show. So in these graphs, the orange line shows sort of a naive RL algorithm learning from scratch. It's actually the Q-learning algorithm that you guys had on homework 3. And the blue line shows the actor-mimic policy, which is sharing knowledge across the different games. And what you can see here, which is fairly typical for these kind of transfer learning methods, is that in some cases it helps a fair bit. Like, for example, the breakout game learns a lot faster here. And in some cases, it actually hurts. So like, for example, the crazy climber game, it does a bit worse. Why does that happen? Well, because there are different degrees of structural similarity between the different domains. So those domains that have more in common will accelerate the learning for each other. Those domains that are sort of the odd one out will actually end up going slower because the model now has to solve a harder problem. It has to represent the strategies for all the games rather than just for one of the games. So if this domain over here is so different from the rest that you're better off learning it from scratch on its own, then it will probably actually go slower if you force it into a multitask setup. But for something like Breakout, if it's structurally similar to a bunch of other games in the set, it might actually go faster by sharing knowledge across the games. All right, now when you train a policy on multiple tasks like this, one thing that we might want to ask is, how does the model know which task to do? In some cases, this is kind of obvious. So, for example, if you're playing the Atari games, you can just look at the screen, and if the screen shows Breakout, then you play Breakout. If it shows Sequest, then you play Sequest. You can just tell right from looking at the screen. But that's not always the case. Sometimes you might want a policy that does multiple different things in the same environment. So if you have a robot, and that robot sometimes needs to do the laundry, and sometimes it needs to go do the dishes, it can't just tell what it's supposed to be doing directly from its observations. So we have to somehow modify the process to make it aware of which task it's supposed to be solving. Now, the idea here is actually going to be very simple, and some of you might have already figured this out. You can associate a context with each of these tasks, and context is just a fancy word for some piece of information that tells you which task it is. So it could even be just an integer that says 0 for dishes, 1 for laundry, or a one hot vector that has the first entry for dishes, the second entry for laundry. And you just condition your policy on that. So a standard policy is a distribution over actions conditioned on states. A contextual policy is a distribution over actions conditioned on states and the context. And the nice thing here is that this just reduces to a standard RL problem, where you now simply define an augmented state space. We'll call it S tilde, which is formed by concatenating the state S and the context omega. And then you just treat that as the state space, and you can plug that into any RL algorithm pretty much without modification. And this is something that people have done quite a bit of in robotics, computer animation, other application domains. So you could have a context, for example, that says, where should this robot put this Lego block? Which direction should this walking robot walk in? Or for this little hockey playing robot, where should it hit the puck to? Like, where's the goal located? So these are all contexts that you can provide to your policy. We're actually going to talk about contexts a lot more next week when we talk about meta learning, because for these kinds of policies, the context is easy to design and provide by hand. In meta learning, we'll actually learn the context itself. So we'll see that next week. All right. The last thing I'm going to discuss in the last few minutes is actually some architecture design decisions that are particularly relevant in a multitask setting. So far, whenever we talked about multitask learning, we always had as our goal to build one single neural network for all the tasks. So with the Atari games, our goal was to distill all those policies into one network that could play all the games simultaneously. But sometimes that's just not practical. Sometimes different tasks actually have maybe fundamentally different inputs. Maybe in one task, you're driving a car using a camera. In another task, you're driving a car using LiDAR. It doesn't really make sense to feed those into the same network because they're essentially different data types. And maybe in one task, you're controlling a robot with 2 arms. In another task, you're controlling a robot with 5 arms. Right? It doesn't make sense to have the same network necessarily doing both. So can you design architectures that can reuse parts across different tasks and then reassemble those parts depending on the data types for the task? So for example, we could have one component of a network for processing camera images, a different component for processing LiDAR images, one component for driving a car, a different component for driving the airplane. So if we wanted cars with cameras, we put the camera part together with the car part. If we wanted planes with LiDAR, take the LiDAR part, put it with a plane part. So there's a pretty cool idea that enables something like this called modular networks. It was actually first explored for supervised learning tasks. I'll explain sort of the computer vision application first, and then I'll discuss how it can be applied in a reinforcement learning setting. But it's, again, just like with the other transfer mechanisms, it's pretty much a direct mapping. So this is an image from this paper by Andreas et al. Called Neural Module Networks. The goal in this paper was to answer questions about images. So this is a standard computer vision task. You get a picture, and you get a sentence in English, like, where is the dog? And typically people would read in that sentence using some kind of LSTM or some kind of recurrent network, read in the image using some kind of convnet, and then produce the answer. The idea in this paper was that there is quite a bit of structure in the description of the question, and that structure might inform what the convnet actually needs to do. And here they take this idea to a very literal extreme, which is that they actually use the sentence to directly select parts of neural networks to stitch together. So if the question is, where is the dog? Then maybe you can figure out that you need a where is module and a dog module, and you staple them together. So the dog module finds the dog, the where module outputs a word in English that describes the location. This is maybe easier to explain with a simpler example. So here the question is, what color is the tie? And then what they do is, it's a little bit of an engineered solution, but the idea is they actually just parse the sentence, pull out the parts of speech, and they figure out that you need to localize something, which is a tie, and then you need to classify the color. And then they have modules for classifying colors and modules for localizing objects, and they say, localization module, find the tie, classifier module, tell me the color of whatever the localizer found. So the localizer outputs a heat map and a tensional map over the tie, and then the classifier just looks at the color. Yes?
Isn't it pretty unscalable if we're expected to have a bunch of modules in that? Why can't we just feed the LSTM representation, for example, to help out the content?
Right. So the question was, well, doesn't this kind of get a little bit unwieldy if you have to select all the modules and so on? And the answer is that, yeah, that's definitely a limitation of this thing. So in this case, they don't actually have a solution for how to automatically generate these things. They just manually select a few basic primitives using their knowledge of the structure of the question answering task. Now, in general, actually, how to design these modules fully automatically is an open problem. So far, all the stuff I'll discuss selects them by hand. All right. So here is the kind of a simple way to map this idea onto reinforcement learning. If let's say you have a few factors of variation among your domains, maybe one factor of variation is what task you're doing. Maybe you're opening a drawer or pushing a block. And another factor of variation is who's doing that task. Is it a robot with 3 links or a robot with 4 links? You could imagine other factors of variation like, is your input images, or is your input depth maps, or is your input something else? Whatever factors of variation you have, you can kind of arrange them in this little matrix, and you can say, well, there are different combinations of these factors of variation. Maybe I've seen this robot open this drawer, this robot push this block, and so on. And ordinarily, you would have a different policy network for each one of these that takes in the state and outputs the action. But what you can do is you can actually decompose it between the factors of variation. So if the factors of variation are the task and the robot, you might have a little task-specific piece and a little robot-specific piece. And there's a different robot-specific piece for every robot, and a different task-specific piece for every task. So while there are 4 different combinations here, you would only need 2 different modules. And then you train on some of those modules or some of those combinations and test on others. But the crucial idea is that the training is still be end-to-end. So the actual interface between these modules at that point is actually entirely learned. The robot modules simply learn to interpret whatever the task modules learn to produce, with the goal for training the whole thing always being the final performance of the task. So you get this sort of emergent interface as a result of this, and then you go and test on a new combination that you haven't seen before. And this would produce, either a policy that works immediately or a policy that serves as a very good initialization for fine-tuning. Now, in practice, how well this works depends crucially on two things. The first thing is how many different values you actually have for these factors of variation, because if you have too few, then you can actually essentially get overfitting, where your lower module simply produces two completely separate sets of outputs for the two possible downstream modules. But if you have 100 possible downstream modules, then the lower module needs to actually consolidate that knowledge into a single representation. The other problem is that if your bottleneck between these modules is too large, meaning that it has very large information capacity, then you might overfit even if you have lots of tasks. So in practice, you need to use some kind of regularization technique to limit the capacity of the bottleneck layer. And this can be as simple as reducing its dimensionality, or as sophisticated as some of the techniques from variational inference that we discussed before. So here's a little demo of this in action. So here there are actually three different robots and three different tasks, and there's one unseen combination, which is a robot with, I think it's 4 links pushing a little red cube. And here is that robot, sometimes pushing it successfully and sometimes not, but generally doing a decently competent job so that it can at least serve as a starting point for some fine-tuning. All right, so quick summary of what we covered. More tasks gives you more diversity, and as we've seen before, more diversity leads to better transfer. It's often easier to obtain multiple different but relevant prior tasks than it is to manually engineer a highly randomized source domain. You can use model-based RL, and that's good because physics are typically conserved across different tasks. You can use distillation to combine multiple policies into one. If you have a policy that needs to do multiple things in the same environment, you might use a contextual policy, where you have a context as an input to tell it what to do. And then there are some architectures that you can use that are more well suited for certain kinds of transfer scenarios, like modular networks. All right, so I'll have some suggested readings. These will be in the slides posted on the website. And then next week, we'll discuss a particular kind of multitask learning called meta-learning, which actually deals with the problem of learning how to learn. So that'll be covered by Kate Rakelli on Monday.